Hi, I'm Menaka Raman-Wilms, and you're listening to The Decibel from the Globe and Mail. The surge in COVID cases has meant new restrictions for most Canadians. The curfew is back in Quebec, and so are capacity limits in gyms and restaurants across the country. Schools in most provinces and territories have delayed classes or gone back to virtual learning. In Ontario, gyms and indoor dining have been completely closed. Schools are online now for at least 2 weeks, and as many as 10,000 surgeries have been postponed to make room for COVID patients. We'd hope this wouldn't happen. The Omicron variant still seems to cause less severe illness than previous variants of concern, but it's so contagious that we're back to trying to flatten the curve so hospitals aren't overwhelmed. This is how Ontario Premier Doug Ford explained it on Monday.
The evidence tells us that about 1% of people who get Omicron will end up in the hospital. That may not seem a lot, and under past waves, it might have been something we could withstand. But Omicron isn't like the other variants. It's much, much more transmissible. So the math isn't on our side. Based on the current trend.
An important way for us to keep track of variants and the ways they've mutated is genomic sequencing. It's how scientists map any genetic code, including that of coronavirus. Today on the show, you'll hear something a bit different. We've asked Globe science reporter Ivan Semeniuk to explain genomic sequencing to us, what it is, how it works, and why understanding the building blocks of COVID-19 can help us prepare for the next variant. You're listening to The Decibel.
In a way, genomic sequencing is like trading in the microscope for like an X-ray machine. It's like looking inside the organism and not just at the blueprint of its genetic code, but that gives you a view of the past and the future. You know, you can look at that genome and ask, where did this virus come from? How did this particular outbreak originate? And also ask questions about how is it changing and where might those changes lead in the future? So potentially it's an incredibly powerful tool. And I think now we're at the point where COVID-19, or the virus that causes COVID-19, has probably been sequenced more than any other organism, or certainly more than any other virus. And that is changing the way I think that pandemics and future outbreaks and illnesses will be approached. And this is going to become really important when it comes time to understanding how vaccines are impacted by the variants, because it's the vaccines that raise antibodies that build up our immunity. If the vaccines need to change to take on new variants or to try to improve our success against variants, it will be important to know exactly where is the virus or new versions of the virus being targeted to ensure that this is going to work. So it's worth reviewing sort of some of the central tenets of molecular biology, how cells work. Our cells all have DNA in the nucleus. The DNA is sort of the instruction set. When those instructions are read, they're turned into RNA, which leaves the nucleus of the cell and goes out into the outer regions of the cell, and then the RNA is translated into proteins. So what the COVID-19 virus does is it enters the cell. Since the COVID-19 virus is carrying RNA, it doesn't have any DNA, it goes straight to that RNA machinery, substitutes its own RNA in place of what would normally be coming out of the nucleus of our own cells. So instead of making proteins that are important for the human body, it's making proteins that are reassembled to form new virus particles, which then go out and infect other cells. So that sequence of RNA that makes up the genetic code of COVID-19, it includes instructions for making the spike protein. It includes, the nucleocapsid, sort of the container that holds the RNA. It also contains a few other tricks, things that the COVID-19 virus is carrying that help disable our immune system And scientists are still learning about, all of the additional equipment that it has to allow it to infect things. And mutations to any of those could actually make a better virus, or a virus that is more able to infect. And then if there's a mutation that does that, it would be rewarded by producing more copies of that version of the virus. If you have an outbreak, say many cases that are related to one case, like a super spreader event, you would expect all of those RNA sequences to essentially be identical. But as time goes on, the virus is changing. There are slight shifts in its genetic code. There's a evolution rate or a mutation rate for this particular virus that's on the order of once every 2 weeks or so. So at any given moment, the virus could mutate, but most of those mutations go nowhere. But of course, as the different strands develop, those mutations are getting magnified because they're all spreading in different directions, and each lineage is kind of exploring different possibilities of the larger evolutionary space that's permitted to that virus. So as those changes accumulate, we can actually see the separate strands, the separate lineages of the virus. There are well over 1,000 worldwide. And, several hundred of those have been detected in Canada. There are many, many hundreds of different versions of this virus. Ideally, what scientists would really like to do is look at changes in the genome of the virus and link those changes to specific molecular mechanisms. I mean, the virus is a little machine that gets into our cells. So how is that machine changing, whether it's the spike protein or other parts of the virus? How is it changing to improve its ability to infect us? Even though the variants haven't been stopped or contained, basically as they emerge, we see them spread around the world. So if the goal is to stop a variant, well, we really haven't seen that happen. However, it's been incredibly powerful to have the warning that these variants are emerging, and those warnings have guided public health officials in terms of when to clamp down, when to improve measures for distancing or masking or other ways of reducing, and also to understand how the dynamics of the pandemic may be changing. And you can see how that caught countries by surprise a little bit when the variants first appeared. By then the pandemic had been around for almost a year, and you had a sense that public health officials were maybe getting used to, okay, this is how it works when we have the pandemic. This is how effective these public health measures are. And of course, the variants were a bit like a high tide that overcame those barriers, and we saw the pandemic start to spread again. So it really gives you a sense of how much more you need to raise your public health measures if a variant with higher fitness is working its way through the population, and also to know which features of which variants we need to worry about. There are things that scientists worry about that keep virologists up at night, where it would be far better to have as current data as you could possibly have. So one possibility is recombination, where you have two separate lineages, two separate variants of the virus. If two separate variants infect the same host at the same time, there's a possibility that they could swap genetic information, and it kind of leapfrog evolutionary space in a way, kind of move the virus into a new domain where it might contain some of the worst properties of both those other variants. So, at one point that was a concern, for example, in British Columbia, where people may remember both the alpha and the gamma variant were on the rise in the spring. And there was a real concern there that something could happen that might not be caught quickly enough to detect a problem before it starts to spread rapidly. And in fact, just in early November, mid-November, a paper was released that was maybe one of the first to try to grab a sense of what the Delta variant is doing in Canada. So this was a cross-Canada paper. It was drawing on a whole large number of genomes and really showing how Delta is diverging into separate lineages, how those lineages compare to each other. And in particular, there's one AY.27, which is almost unique to Canada. So it's important for us to keep track of it because it's not very prevalent elsewhere in the world. In Canada, most of the sequencing is done in provincial health labs or by sort of a series of laboratories that might then fit into a province's public health system. For example, in Ontario, that's the case. The largest sequencer in Ontario is the Public Health of Ontario Laboratory right in downtown Toronto. They've now sequenced the COVID-19 virus over 40,000 times, more than any other lab in Canada. But they're also bringing in information from 4 other regional centers around Ontario. So it's a huge amount of data. Other provinces are doing the same thing, Quebec, British Columbia, and then there are kind of collectives for the prairies in Atlantic Canada. In addition to sequencing the genomes, they also have additional information. Where did these cases come from? What was the gender? What was the age? What was the vaccination status of the individual? What was the reason why the sequence was taken? In Ontario right now, for example, if there's a travel case, if there's something else that might prompt, we better sequence this genome just to see if there was a particular outbreak or some unusual circumstance. On top of that, the province is now randomly sampling 1 out of every 4 genomes just to get a sense of, randomly what's happening, what is the pattern of evolution at this point in time. So the provinces are, building up these genomes, and in theory, all of this information then is going to the National Microbiology Lab, which is a federal facility, which is curating the genomes, and ultimately this is going to a big database where Canadian scientists can freely access the data, analyze it, and work with it. But in practice, it's been very slow, and in fact, it was taking months, actually, for genome-related data to get from a provincial lab to a place where a scientist could access it and work with it. And when you're talking about weeks or months, you're really not getting a snapshot of what the pandemic is doing. And the problem is, if the provinces are operating like separate countries in terms of doing their own genomic sequencing, those are very small population bases. So the data could be influenced by noise, maybe it's just randomly that one particular lineage has grown. Maybe it doesn't really have an advantage. You really need to look at more data, ideally across the whole country, to have more confidence in the patterns that you're seeing. And, public health labs also have a lot of other things on their plate while a pandemic is in full swing. So for them, it hasn't been as high a priority. And that kind of tension has characterized the Canadian effort. The future of the virus is really dictated by its genome in combination with what the environment is throwing at it. So increasingly, it's being hemmed in by vaccines. So, to the extent that there's going to be more evolution, some of that may be in response to the fact that, at some point, if enough people are vaccinated, then that vaccinated population is the only place where the virus will have left to go. Now, there are many, many places in the world where the vaccination rate is still very low. So there are lots of people still to infect that haven't been vaccinated. So for the next little while, that's probably still going to be the main driver of evolution. Also, it's worth saying that vaccines are very effective at shutting down evolution, because if a vaccine is working well, it's really slowing down the number of virus particles that are entering cells, since the antibodies are stopping the infection before it can start, essentially. So, maybe some virus particles will get through, there'll be a mild infection, but there won't be a serious infection. But the overall result is fewer cells are getting infected, fewer virus particles in the system, and so fewer opportunities for mutation. So in a way, a vaccine is a very effective wall for a virus, more effective than, say, drugs or treatments that come after an infection has already started. So even though it's good news, for example, that there are some new therapies that are being rolled out, antiviral medications, and of course we've had monoclonal antibodies and other ways of treating COVID, those are actually more likely to promote mutation than a vaccine would, because they come on the scene after the virus has already started replicating. So all of those things could play a role into which way the virus goes, because it's looking for escape routes through these defenses that we are throwing up. So I guess the key thing is going to be, in countries that have a high vaccination rate, looking for signs of vaccination escape. In countries where there's a low vaccination rate, looking for sudden increases in the rate of cases to see if a new mutation or a new variant has arrived with a substantial advantage. It will have an influence on the length of the pandemic and on what happens if we shift into sort of an endemic situation where we're trying to manage this virus in the long term. And is it one that's going to be continuing to change, or one where we can effectively control it, for years to come? That's an open question.
Before we go, an update. Here's Minister of Indigenous Services, Patty Hajdu, on Tuesday.
Canada's decisions and actions harmed First Nations children, families, and communities. Discrimination caused intergenerational harm and loss, and those losses are not reversible. But I believe that healing is possible if we look face-on at the harms caused, if we compensate, and most importantly, if we end the discrimination once and for all.
A $40 billion agreement has been reached between Ottawa and Indigenous leaders. The deal is to compensate First Nations kids who were harmed by an underfunded federal child welfare system. Half the money is for compensation, and the other half will go towards reforming the system. The final details of the deal are still being negotiated. Plus, on Monday, Theranos founder Elizabeth Holmes was convicted on 4 counts of fraud and conspiracy for misleading investors about a revolutionary machine that could test a drop of blood for all kinds of diseases, except the machine didn't work. Holmes faces a maximum of 20 years in prison for each conviction. Okay, that's it for today. I'm Menaka Raman-Wilms. Our producers are Madeline White and Cheryl Sutherland. David Crosby edits the show. Kasia Mihailovich is our senior producer, and Angela Pacenza is our executive editor. Thanks to Ivan Semeniuk. You can find more of his work at theglobeandmail.com. You can also email us at thedecibel@globeandmail.com. If you want to reach me, I'm on Twitter at MenakaRW. And if you haven't already, please follow The Decibel wherever you get your podcasts. Thanks so much for listening, and I'll talk to you tomorrow.